Alright, silly people, here's the situation. This time we're going to be proving that the set of all square integrable functions constitutes a vector space. That is, in set notation, that the set of all f of x such that the integral of the square modulus of f of x from a to b dx happens to be less than infinity. We're going to prove that that constitutes a vector space. And for it to be a vector space, it has to be closed under a couple different kinds of operations. The first kind of operation it has to be closed under is scalar multiplication. That is, if you, let's say, have a function called g of x, which is some constant c times f of x, where I'm defining c to be some complex number that's less than infinity, then is this still in the set is the question. Well, let's actually just calculate the integral from a to b of the square modulus of g of x dx, which from our definition we can pull the c out of the mod squared, so it's the mod squared c integral from a to b of the mod squared of f of x dx, which by definition this is less than infinity and this is less than infinity, so the whole thing is less than infinity, so it is closed under scalar multiplication. The next one, which is arguably more difficult, is vector addition, which is kind of crazy. So that is saying if f of x is equal to some function g of x plus h of x, where g and h are both square integrable, then is the sum of them also square integrable? Well, let's just check. So it's going to be the integral from a to b mod squared f of x dx, in this case, is equal to the integral from a to b of the mod squared of g of x plus h of x, which you can expand the mod squared because you know that this is going to be integral a to b just the complex conjugates of the functions times the non-conjugated versions of the functions dx, and you can distribute the multiplication so that you have integral from a to b. You're going to have one term proportional to mod squared g of x and another term proportional to mod squared h of x. My cat is really being nice to me right now. Plus a term proportional to g conjugated x times h of x plus h conjugated of x g of x dx. That's a lot of integrals, but we can split them up because this is going to be the integral from a to b of g of x squared dx, which happens to be less than infinity by definition. Also plus the integral from a to b of h of x squared dx, also less than infinity by definition. Plus a couple different integrals. This is now integral from a to b of g star of x h of x dx, plus the integral from a to b of h star of x g of x dx. So the proof is complete if we can prove that this entire quantity here is also less than infinity. And to do that, we can use something that was talked about in the beginning of this chapter called the Schwarz inequality, which says that, and let me write this in blue, it says that the modulus of the integral from a to b of f star of x g of x dx is less than or equal to the square root of the integral from a to b mod f of x squared dx, integral from a to b mod g of x squared dx, right? And so we also know that this quantity is less than infinity, and this quantity is less than infinity, so the whole thing has to be less than infinity. So that's pretty cool. So with that in mind, integral a to b of g star of x, h of x, at least the modulus of it, happens to be less than infinity, and also the modulus of the integral from a to b h star of x, g of x dx, also happens to be less than infinity by the same maxim. So the whole thing is less than infinity, so is closed under scalar multiplication. And so therefore, yes, this set of all square integrable functions does constitute a vector space. That's pretty awesome. The next part of the problem is to show that the integral in equation 3.6, which is the inner product of f with g, is being defined as the integral from a to b of f of x, f star of x, g of x dx, constitutes an inner product. And for it to constitute an inner product, it has to satisfy a lot of different conditions. So I'm just turning to the linear algebra section of the book so I can remember what those conditions are. And there they are. This is an inner product if it satisfies that the inner product of beta with alpha, or I guess that the inner product of f with g is equal to the square modulus of the inner product of g with f. It also has to satisfy that the inner product of f with itself is greater than or equal to 0, with the caveat that if the inner product of f with itself happens to be 0, then that can only be true if f happens to be 0. Also, it has to satisfy, like, I forget what the name of this property is called right now, but basically you can distribute the inner products multiplicatively. So this thing, this vector, times this sum of two vectors ends up being b alpha beta plus c alpha gamma. Right? If it satisfies all three of these, then it does happen to be an inner product. Right. So what we can do is we can see what the inner product of g with f is in integral form. It's the integral from a to b of g star of x, f of x, dx. And then if we take the complex conjugate of this guy, then we're going to have the integral from a to b g of x, f star of x, dx. So this is just the reordered version of integral from a to b of f star of x, g of x, dx, which happens to be the definition of the inner product of f with g. So this is true. The inner product of f with itself happens to be the integral from a to b of f star of x, f of x, dx, which we know happens to be the integral from a to b of the square modulus of f of x, dx, which, if it's a square integrable function, then it's less than infinity. But it is positive, greater than or equal to 0, so this is true. If the inner product of f with itself is equal to 0, then, I mean, yeah, the only integral that is 0 is the integral of 0. So it is just going to be, then this is interchangeable with the statement that f of x is equal to 0. So this is true. Finally, we need to prove, if we define it like this, the inner product of f with b G plus C H equals B times the inner product of F with G plus C times the inner product of F with H. So that's going to look like the integral from A to B of F star of X. And then it's times this B G of X plus C H of X dx. And then you just distribute the function through. So this is going to be now the integral from A to B of B F star of X G of X dx plus the integral from A to B of C F star of X H of X dx. And then you can pull the constants out of the integrals. So you get B times F with G plus C times F with H. So yeah, this is true as well. So it is an inner product, which is fantastic.